All right. Hello, everyone. Hopefully you are all doing well tonight. Sorry, this is getting out a little bit later than I was anticipating, but such is life. So we're going to, just like we do before all of our tests, be going over every single problem type on the study guide. Um, Just like usual, this is not going to be me going through every single question, but I do want to take a look at every single style of question that you could see, so that you guys have kind of a comprehensive overview as to what this could be. Go away. Stop. All right. Sure that our lights. Stop. All good to go. Cool. All right. So we are going to start with number 1 here. Double check to make sure. Yeah, should be good. We're going to start with number 1 here. So for number 1, we are told that we would like to know how large of a sample of trout must we take with a 93% confidence interval so that our sample is off by no more than 0.4 inches, given that the standard deviation is known to be 2.1 inches. All right, so we are, in this case, looking for our sample size, or value in this case of n, and so we should know n is equal to, in this case, our z of alpha over 2 times sigma over the square, sorry, again, mixing my formulas, divided by the error, all squared. All right, so 3 components here. We need our z of alpha over 2, we need our sigma, and we need our error. These two are just given to us, which is nice. In this case, we are told that our standard deviation is 2.1 inches, and we are told that we want to be within 0.4 inches of the mean. So this will be 0.4 right here. Now, 93% is a little bit of an unusual z-score. So we are going to be going to our inverse norm. And in doing so, I get that the z-score that we should use is about 1.81. So this would be our second bars inverse norm. For the area is that 0.93. And we want to be centered. All right. So we get in this case that n is equal to 1.81 times our standard deviation, which in this case is 2.1, divided by our error, 0.4, all squared, which comes out to be 1. I get that this is about 90.3. Now, 90.3 is not a sample size that we can take. In fact, this is the minimum allowable sample size. As long as we're bigger than 90.3, we are in the clear, right? We could use 100 and we'd be perfectly fine. We could use 1,000, we'd be perfectly fine. As long as we don't go below 90.3, we should be perfectly fine. In this case, generally speaking, with these, you will be asked to find the minimum sample size that we could possibly see. So the smallest number that is above 90.3 that we could use would be this n of 90. Sure that we all right, so continuing right along here. We're going to be taking a look at number 3. In this case, we were told that we are trying to estimate the mean. So we want to know so mean number of blood tests given to patients each day. Hospital records show that in a randomly selected sample of 100 days, the average amount of blood, so in this case, the X bar is 80, with a standard deviation, which we'll go ahead and call realistic. Okay, so here it doesn't specify whether this standard deviation is from the population or from the sample. It asks us, essentially it gives us like, hey, sigma is equal to like so and so. But I'd actually argue that the way this reads, it certainly feels like that 0.87 is coming from the sample. Now, on the test, the language is going to be unambiguous. You're going to know that it is in fact a population standard deviation, if in fact that is what I give you. But in this case, it actually doesn't even matter, because what we're going to find is that our value here, that our sample size is big enough that we don't actually care. In particular here, we're saying that our sample size is 100, collecting a sample that is 100 days large. And we're being asked to construct a 95% confidence interval. And actually then the follow-up, so construct the 95% confidence interval and then state what the margin of error is. All right. So I don't have with me my fancy calculator that'll let me do this, so I'm going to have to do this by hand. If I did have access to my calculator, this is going to be a Z interval. You could actually also here use a T interval, because again, we don't really necessarily know the population. It'll be clear if I'm giving you sigma, and I would argue that here it's not. But here it really does not matter, because our n is large enough that the t value and the z value are functionally going to be exactly the same. Now, to be completely transparent, I will say, if I had given you clearly that we were referring to sigma here, so if I told you the population standard deviation is 8.7 and you turn around and you use a t-interval, you are wrong. That is incorrect. We do not use a t-score. In that case, we would want to use a z-interval. But in this case, I would say that it is ambiguous, and I would also say that it ultimately isn't going to really change our results by enough for us to be overly worried. So what is this going to look like? Well, for you guys, this would just be stats into tests, into your Z interval, where you then enter in all of this information, and it's going to tell you exactly what it is. For me, I'm going to need to use my formula of X bar minus the EBM to X bar plus the EBM, where the EBM is equal to our critical value, either Z or T, times our standard deviation divided by the square root of n, and that could be S or sigma. That's fine. Right? In this case, we know that we are looking at a 95% confidence interval. And so the t-score or the z-score, I'm going to use the z-score here, should be very, very close to 1.96. It really should be about the same thing. I'm going to use the z-score here at 1.96 because our n here is greater than or equal to 30. And so our error equal to this 1.96 times our standard deviation, which we were told is 8.7, divided by the square root of 100. This, so 1.96 times. I get that this error is equal to 1.7. We'll call it 1.7. And so what is my confidence interval going to look like? Well, it's going to look like from 80 minus 1.71 to 80 plus 1.71, which should be from 78.29 up to 81.7. All right. Let's now take a look at number 4 here. For number 4, we are told yeah, that's fine. So for number 4, we are told that in a survey, 530 out of 800 people interviewed who said that they shop in a large, the downtown area at least once a week. We're trying to figure out the true proportion. So we want to know, how have I been phrasing it? No. The true proportion, P. All right. In this case, how would I know that I was looking for proportion other than the fact that there is the buzzword like proportion or percentage or something along the lines? Well, the first thing to note here is that this is essentially binomial, right? Where we're going to have people who are either yes or no, who are like satisfying a condition or not satisfying a condition. So this is like what fraction of the people satisfy this condition, what fraction do not. Contrast that with what we saw in number 3, where what we are given here, this 80 is not 80%, right? This is saying that on a typical day, we're taking literally 80 blood tests. We're not saying that we're taking a blood test on 80% of the days. Right? So how do we figure this out? One thing that I really, really, really want to impress, right, is that we have a lot of calculator functions. And I have a lot of people who are very, very confused or who have expressed to me confusion about when to use which test. And I really, really want to make it clear that this one prop z interval business that we are introducing is very, very much not necessary to what we are doing, right? So you absolutely can, in the calculator, go to stats and tests and the one prop z interval. That is totally fine. It's fairly straightforward, not bad at all. But we don't have to, right? We also can do exactly what we have seen before, where we find x bar, where we find s, and where we find our z-score, and we run from there. Now, in this case, x bar is going to be our sample proportion. Okay, so what is our sample proportion? Well, in this case, we have 530 successes out of 800 possible individuals. So 530 out of 800 works itself out to be 0.6625. Now S, the way we calculate S for our proportions, this is the square root of p hat times q hat, which is equal to, well, this is the square root of 0.6625 times, well, we want q hat, probability of not kind of being a success here, which would be 1 minus 0.6625. And then our z-score here, we are told that we are looking at a confidence interval of 92%. And so let me do my inverse norm business. Apparently, the critical value here is 1.75. And so doing the exact same thing before, this was x bar minus the EBM to x bar plus the EBM. Or again, you could just use your z interval, or you could use your one prop, whatever. However you want to do this is totally fine. But again, like these calculations by hand are not particularly difficult. It's the same formula over and over and over and over again, where our EBM technically here it might be better. You'll see on your formula sheet it says EBP because we do want to know a proportion, but like we want to know the expected value for a proportion. That is also a type of average. But this is going to be equal to our z-score times S over the square root of n. It's going to be equal to 1.75 times S, that's our square root, 0.6625 times 1 minus 0.6625 divided by the square root of, we said we surveyed 800 people, which tells us that our error is this is going to be 0.6625 times minus 0.6625 divided by, we said 800. All right, I get that this is equal to 0.0293 rather. So we'll call it 0.02. That's fine. So what does this look like? Well, this is going to be our mean, which is our p hat, which is our 0.6625 minus the 0.029 and our 0.6625 plus the 0.029, which works itself out to be we'll do this, so 0.633 to 0.692, or because it asks for decimal or percent, from 63.3%, which we don't really need to include there, up to 69.2%. So we know that the true P lives here like 92% of the time. All right. Let's take a look at yeah, we'll do number 8 next. Eight. So we are told a random sample of 28 school districts showed that the mean number of students per teacher. So again, trying to construct this confidence interval looking for our mu. We're told that the average that we see from our sample is this 25.1. And in this case, we're actually told that the variance is equal to, actually not population variance, the variance from the sample is equal to 10.24, where n in this case is equal to 20. Okay, so first thing that I want to note here is that we don't know sigma. And n is small, which means we need to use a t interval. Right? This is really the only instance in which we need to use a t interval. We both don't know sigma, and our value of n is particularly small. So we're going to need to figure out what t of alpha over 2 is equal to. The other thing to note here is that we have not been given the standard deviation. We have instead been given the variance. Good news for us, that standard deviation is just equal to the square root of the variance, which in this case is 10.24. Square root, this is equal to 3.2. Right. So for you guys, again, this would just be stats tests to t interval. And for figuring out the appropriate t-score, certainly I will ask you to do that. This would be second bars into our inverse t, where you just have to remember that the area is half of leftover. So for instance, in this case, we are looking at a 98% confidence interval, which takes us to 0.02 on the outside, divided by 2 gives us 0.01 as our area. A lot of people are going to use 0.98 for their area, and they are going to miss a lot of points because of it. I would recommend using the correct area, and instead of missing the points, getting the points. So for our t-score here, let's see, this is 98%, 27. So freedom. Again, I don't have my fancy calculators, so this is not as straightforward for me finding this particular t-score. And also my computer is exploding, which is good. Very good. Let's do this. All right, I'm having to do it the old-fashioned way. So I'm looking at 27. We wanted a 98%. So for two-tail, that would be here at 27 degrees of freedom. I believe I am seeing 2.473. I do believe. All right. So exact same idea. Error is the exact same. Our confidence interval is the exact same. In this case, we're using the t-score though instead of the z-score, but again, literally the exact same thing. We have one formula, literally just one formula that we use for every single problem that we are doing. So this error is equal to 2.473 times our standard deviation, not the 10.24, but the 3.2 divided by the square root of 28. I get that our error is 3.2 divided by 28 to the 0.5. I get 1 point, we'll call it 1.5. 1.496. We'll say 1.6. And so we want our mean plus that, we want our mean minus that. So we'll do that. Say 21 minus this. I get 23.6 to 26.6. Very good. We'll do a brief pit stop. Again, because I don't have a calculator, this is significantly harder for me to do by hand. So I will leave this one as an exercise for the reader, but we'll talk about it. So for number 10, we are again being asked to construct a confidence interval for mean. Estimating, looking for a confidence interval for mu. In this case, though, instead of being given information, so normally we would want to find, hey, what is X bar? What is S? What's our T or our Z score? In this case, we're just given a bunch of data. We're given the sample that we're trying to figure out. We're trying to construct a 94% confidence interval, which is certainly a little bit awkward because that is generally speaking not going to be one that we see on our table. So I will certainly struggle with this, which is part of why we're going to leave this as an exercise 3. But not too horrible here. So what you guys are going to do is you're going to go to stats, you're going to go to edit, and you're going to fill in your L1. From there, you have two options. You can either go to stats, calc, one variable stats, and it will gives you X bar and SX to use. Exciting. It'll calculate that standard deviation and that mean for you. You don't have to do anything for it. Note that you are not using our that we are not using sigma x. All right, this is a sample, and so we want it to be treated as a sample. We could then, if we wanted to calculate the t-score, we could do inverse t for our t-score if we needed to. Notice t in this case because our n in this case is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points that we have. Or alternatively, we could go to stats after we've entered in the data. We can go to tests, go to our t interval, and we can just use data from L1 instead of X bar and X. They do the exact same thing. All right, there is not an advantage to doing one over the other. If you don't want to worry again about extra calculator functions, then you can just use that one variable stats in order to figure out exactly what's going on, and you'll be totally fine. But this is, of course, another perfectly viable way to do it. All right, one final one to wrap up. We're going to be taking a look at number 11 here. So in this case, we are trying to estimate with 95% confidence population proportion of adults. We need to make that estimate be accurate within 4% of the population. In this case, we are looking for our sample size. Again, that value of n. And we've already done this. We already know what n is. N should be equal to our z-score times either sigma or s, depending on what we have, divided by that error, either EBM or EBP, whatever, exactly the same thing, so it doesn't really matter, squared. In this case, though, we are given proportions, and so we can clarify a little bit what s is equal to. Well, s should be equal to our p hat times our q hat. Problem that we see here is we don't have a p hat and a q hat, at least not for the first example. So we have no previous data. Which means we have no p hat or q hat. Which means we are going to essentially, the goal here is not to underestimate n. So to avoid underestimating our sample size that we'll need. Because if we get too big, that's fine, right? If we take a sample that's 10 too big, that's great. Nothing, no harm, no foul. But if we take one that's too small, then all of a sudden we're in trouble. So to avoid underestimating n, we are going to maximize s by setting p and q both equal to 0.5. All right. Additionally, we are looking at a 95% confidence interval. Z-score should be 1.96. And we are told we want our error, EM, EBP, whatever, doesn't really matter, to be equal to 4%. So 4%, 0.04. So n should be equal to our 1.96 times square root of 0.5 times 0.5, all divided by 0.04 squared. So the value that I get for n square this, I get that n is 612.6, which we know is going to round up to 613. So that is the minimum possible value that we could see for n.
Oh, I did 1.98, not 1.96. I was wondering. I was like, that answer didn't.
Yeah. Sorry. Plugged it into my calculator wrong. Did 1.98 instead of 1.96. I got 600.25. There we go. That looks more correct, which rounds up to 601. Can't round down, can't be lower than 600.25. Now for B, we're asked to do the exact same thing, except we have now a previous data sample that tells us that P hat is equal to 0.47 and that Q hat is equal to 0.53. And then we're asked to kind of compare the results. What are we going to get? That's different. Intuitively, we should kind of anticipate what difference this is going to make. If we are changing S at all, it's going to be smaller. We picked 0.5 for the purpose of making S as large as we possibly could. Any kind of change that we make to P hat or Q hat is just going to lower the sample size. The more we know about the population, the smaller a sample we are allowed to take because we have some kind of foreknowledge. We can be a little bit more precise than what we would otherwise be able to be. So exact same thing, exact same deal, except instead of 0.05, we are instead going to use our previous data of that 0.47, that's 0.53, divided by our 0.04. I want all of that squared. 7 times 3. And from this, again, I don't know that I trust that. Let me double check with my parentheses. Yeah, looks legit. All right. I get that n is equal to, and if this is slightly off, I do apologize. I am working with the technology that I am able to. 588.48, which of course is going to round up to 589, which should have been predictable. All right, hopefully that was helpful. We are going to call it there. If you do have any questions before the test tomorrow, please feel free to reach out and ask. Although, with how late this is getting up, I am aware that that might not be all that feasible. But regardless, I wish you all the best and wish you guys the best of luck tomorrow going into our test. Take care, you guys.